Hello， 大家好，我是交警布布。之前我发了一个关于毒品的视频，然后引来了广泛的讨论。只不过引来很多讨论的是我的妆容。很多人不仅在我那个视频下面破防了，还在跑到我3年前的视频那边去破防。我并不想在原视频下面牵扯或者讨论太多关于这方面的内容，因为我认为毒品是一个很严肃的话题，本来就不应该被其他话题所带跑偏。但是秉着大家都有言论自由的原则，我不会删评论或者清弹幕。但是看在大家都这么想讨论我的妆容的情况下，那么我就好好跟大家讨论一下化妆这件比毒品小很多的事情。大家可以先来简单看一下这些评论什么的，然后很轻松的就能总结出来他们破防的点。在这些人看来，我的妆容因为眯眯眼，所以肯定是迎合美国人对中国人的刻板印象的丑妆容。身为一个中国人，我能够理解为什么中国人喜欢嘲笑外国人走火入魔的政治正确，因为过度追求正确反而加深了刻板印象，和他提升所有群体包容度的这个本来的本意，它完全背道而驰，所以我们会对此捧腹大笑。但是我们中国人不在乎政治正确的底气是什么？是我们中华民族强大的文化底蕴，我们5000多年的历史积攒下丰厚的文化带给我们的自信。所以当我们看到外面其他的文化的时候，我们不是排斥，而是做出一个文化大国该有的反应，也就是包容。在这样一个文化底蕴下长大的我们，这样的中国人，我们可以包容各种各样的人，脸大的人，脸小的人，高矮胖瘦，或者眼睛大以及眼睛小的人。可是当美国人对中国人的眯眯眼的刻板印象传到这边的时候，很多中国人却反而开始排斥眼睛小的人。因为美国人对中国人的刻板印象是眯眯眼，所以有一些中国人就把眼睛大当做了政治正确，却忘了我们身为文化大国人民真正该做的事情。我们应该做的事情一直以来都是包容拥有任何外貌特征的人。我现在是素颜，大家可以看一下我的眼睛，它就这么大，它从小就这么大。我从小到大一直都不是一个眼睛很大的人，但是因为是在一个包容的中国这么一个环境下长大的中国人，我从来没有因为我的眼睛小而感到过自卑。因此我从来没有想过通过化妆把我的眼睛给画大。我一直都是有自信的，所以我不会因为区美国的刻板印象而感到自卑，更不会因此而试着把我本来就这么大的眼睛给想办法给搞大。相反，如果觉得我的眼睛小就要强迫我把眼睛画大的人，你们何尝不是推动政治正确、消灭社会包容度的真正最身为女生，我同意女生化妆就是为了给别人看的这一说法，我也同意任何人化妆都是为了给别人看的这一说法。毕竟我不能把眼珠子抠下来看看自己再安回去。但是我化妆并不是为了取悦你。首先，我化妆的目的不一定是为了你，我可能会搞一个类的仿妆，然后你可能会觉得哇无法接受。但我本来化妆的时候想的就不是你，和我一样喜欢看鬼灭之刃的小伙伴自然会欣赏我的妆容，我也可能会搞一个唐朝妆容，你又无法接受了。但是喜欢唐朝文化的小伙伴自然会觉得喜欢。其次，我化妆并不一定是为了取悦别人，比如说当我去见一个喜欢白又瘦并且喜欢蹬鼻子上脸的油腻男的时候，我可能会画一个凶一点的欧美妆。再比如说，当我要去见一个我从来没有见过的人，并且想要快速向对方传达我的个性的话，我可能会搞一个粉色辣妹妆。 对方可能喜欢，也可能不喜欢，不过我快速传达个性的目的达到了。由此，一个人化妆是给别人看的这个说法虽然是没有错的，但是总有人喜欢曲解这句话，比如女性化妆就是为了取悦男性之类的，这些毫无疑问是没有道理的。最后，化妆这件事情从始至终都是人的自由，我可以在我的脸上放任何我喜欢的妆容，因为这是我的脸。如果你心胸狭隘到只能允许别人的脸上有你喜欢的妆容的话，Well，
自己评判别人的内外的价值，发现自卑到了一个可怜的极点发言精湛，自豪的嘲笑的废物，佩服自己听不见把戏多么践踏搞得你比别人还清楚，要不要你来引路，我比空还坚硬，是你迫不得的结束所有黑的辛苦 ，fake 辛苦，我就是你说那个旁边的信徒，进入禁锢住的金库呀，我眼红呀，仿佛这些天球都会被你掀动呀，丑陋的面容呀，早。没半点仿制，随着逆风挣扎，依旧加点房子。活在沟里的生物就是这样见过死。Yeah, no no no， 我这份教你确实不配有，如同在马戏团看小丑 ，pass off。Hey, so who is the big cut？
Hello everyone, can everyone hear me? Cool. So my name is Jenny, I'm the president of the Cognitive Science Student Association. This Saturday, starting from 10:30 a.m., we are having our 12th annual National Cognitive Science Conference. This time, it's going to be at the Price Center East Barroom. This time, we will have 9 speakers giving us talks covering all the specializations on our Cogs side. Also, we will have 10 labs presenting themselves, including Dr. Wojtek's lab. So if you're interested, I'll pass down these flyers, so please take one and join us on Saturday. It will be PC East Barroom, 10:30 a.m. Thank you.
Great, thanks. One quick announcement. If you haven't enrolled in PackBack, make sure that you do that, okay? And I know some of you have been having an issue with the passcode and things like that. There's an announcement on the website on how to enroll, and there's the passcode in case you need it, right? So make sure you do that this week, because remember, next week is when we start expecting you to provide the questions and answers and things like that, okay? If there are any questions about that, ask the TA, ask me, all right? Let's get that done, please. Okay, so today we're very pleased to have Dr. Brad Wojtek, who's a faculty in the Cogs department. He's going to tell us a little bit about a very exciting new development in the field of data science, I think.
Good morning. How's everybody doing? Woo, all right. As excited as can be, sitting in a 9:30 a.m. class. All right. So, is anybody taking a class with me? Cogs 9 or 108? 1? All right. So, it's going to be pretty boring. You can just like take a nap or go. You've already seen something like this. So, there we go. Oh, that's not right. I'm at the end of my talk. Off to a really awesome start. Here we go. Okay, so who am I? Why are you listening to me, right? So I always find it interesting that you're expected to come to these classes and then you have to listen to somebody that you've never met before and you really have no context for who the person is or what you should be listening. You don't even know, maybe I'm just like one of Jamie's friends off the street. You have no idea what it is that I'm actually doing here. So I run a research lab, run the neural data analytics lab. So I'm a neuroscientist and a data scientist. So this is my group. We have an office over in the Cognitive Science building in the Social Science Research building, in which we have a perfectly harmless box. We go many days at a time before fires break out, and for whatever reason, the undergrads have a bag of emergency lab pants, and I don't know what that's about. I am a zombie expert. So in my spare time, I wrote a book about zombie brains, which was a joke that went on for way too long. That got translated into, I guess that's a decent translation, I'm told. I don't actually know. And it got very well reviewed. Literally hundreds of people have bought this book. And yeah, it was as described, which is really, as a author and a creator, really the best thing you can hope for is a review like this. As described is really what you're shooting for. I did a joke a number of years ago. So for people who aren't familiar, you know when you do like a high school science fair project and you do those like tripartite poster board things and you're like, what happens if you microwave a chrysalis or something, right? Like that's what you do in high school. So every year there's real science conferences that professors from all around the world, and graduate and PhD students and researchers get together. And there's a neuroscience conference every year, except it's like 35,000 people. And it's the exact same kind of, I mean, they're usually not microwaving chrysalises or whatever, but like it's the same kind of idea of like people standing in front of these poster boards, except there's literally thousands of them at a time. And it's like first year PhD students standing next to these poster boards for 4 hours, hoping to God nobody actually walks by and asks them anything. And so one year, my friend and I actually hung up a poster about zombie brains. Like we just pretended like it was real research and we just like stuck it there and ran away. And that's the joke and that's how it started. And that got like really blown out of proportion to eventually got an email from Princeton University Press asking us to write a book about the zombie brain. And so the entire joke was, what if we pretended like zombies were real? You have not been in this class long enough, but as you go through this course over this quarter, every single professor who gives a guest lecture will teach you about Broca's and Wernicke's area and Broca's and Wernicke's aphasia. You will hear that 400 times during the course of this quarter. So what you probably have not yet heard is these are the brain areas responsible for understanding and allowing you to speak. So understanding speech and then allowing you to speak. And the reason that you're going to hear about them 400 times is because they're like classic history of neuroscience and cognitive science topics. And really the only way in neuroscience that we can understand like which brain regions are responsible for what kinds of cognitive functions. What is it that allows us to speak? What is it that allows us to see or hear or move or talk is these 86 billion or so neurons in our head. And for whatever reason, those neurons are organized, those brain cells are organized in such a manner as to allow us to coordinate these behaviors, and they're relatively consistent across people. So the part of the brain that allows me to hear what you all are doing, to see that only half of you are paying attention, to be able to speak to you all while simultaneously like gesticulating, and you know, I'm mostly Italian, so I talk with my hands a lot. Like, these are the kinds of things that can be measured across people. And there are 86 billion neurons in your central nervous system, half of which are in this little part of the brain in the back here called the cerebellum. Literally just means little brain. And those 40 billion plus neurons allow us to do things like complicated movements, right? So I can do that and catch that thing. I'm a professor, that's like a 50-50 chance that I was actually going to be able to catch that. But the fact that I can do that without having to go, okay, it is moving 7.21 meters per second, you know, like this, and then I have to shift my body 17.2%, weight forward this way, rotate 7.1%, shift down 3.2, right? I don't have to do all of that. The fact that I can just do all of these really quick calculations across my body without thinking about them is something that these neurons in the back of the brain do. So half of your neurons in your brain are dedicated largely to just allowing you to move without having to think about it. And how do we know that? One of the only ways we have to know that is by looking at what happens when that part of the brain gets damaged or something goes awry. So the reason, going back, that you're going to hear about Broca's and Wernicke's areas of the brain and Broca's and Wernicke's aphasias is because those were the first modern documented cases where somebody had brain damage that knocked out a very specific behavioral or cognitive function. Meaning somebody had a stroke, which is a disorder wherein blood vessels either get blocked or rupture in the brain that causes neurons to die in a specific region where that blockage occurred. And then when those neurons die, you can no longer do a thing. And mapping what part of the brain's neurons have died in different stroke across people, and what are the behavioral consequences of that, is how modern neuroscience really began. And it's one of the only ways that we can really say for certain that this part of the brain is required to do this thing. So this part of the brain is required for you to see, this part of the brain is required for you to speak, this one to hear, and so on. And so the history of neuroscience is actually kind of morbid in a lot of ways, because the only way that we really learned about this stuff was by first mapping what happens when somebody's brain gets physically damaged. And so when we wrote this zombie brain book thing, right, it's a joke, but it's actually trying to teach like real neuroscience. But if I go into a introduction to cognitive science class or high school, and I want to teach people about neuroscience, and I say, my lab studies the role that neural oscillations play in coordinating information transfer through phase-mediated, nobody cares. It doesn't mean anything. It's like jargon word salad. It doesn't mean anything. I may as well be speaking, Klingon. Anybody speak Klingon? I don't want to offend the Klingon speakers, but it doesn't make any sense, right? Because it's so dense and packed full of a bunch of stuff that you have to have a PhD to understand. If instead I say, okay, why is it that zombies can't talk? Other than, well, it's a bullshit, not real thing, professor. But if you were going to pretend that zombies were real things, why do they move really slowly like this? Why do they go, why can't they run after you unless it's a fast zombie? And that's like a rift in the zombie community. There are zombie communities, and fast versus slow is like a major rift between the two camps. Why can't they do these things? And then you start explaining about the role that the cerebellum plays in coordinating body movements, the role that Broca's area plays in allowing you to understand, communicate, or to produce speech, I should say, and Wernicke's area for understanding speech. The role that the basal ganglia play in coordinating action planning. If I go into a high school classroom, which I am doing next week, I've done this before, and I start talking about these things, you suddenly get 16-year-olds that are arguing about basal ganglia versus cerebellum stuff by the end of the lecture. And so it's a way of trying to introduce complicated topics like what you will be learning in this class in a way that is in any way meaningful, I guess. But it really did get way out of hand. Wired magazine published a science of surviving the zombie apocalypse. But I'm not here to talk about zombie stuff today. I'm here to talk about data science. So UCSD started this new Haliciolu data, and I promise this ties back. I am actually a neuroscientist, and everything the preamble there really does tie back, I promise. A couple weeks ago, UCSD launched the Haliciolu, that's how you pronounce that, Haliciolu, Data Science Institute, or the HDSI. The HDSI is a collaboration. It's a new institute here. It's a collaboration between cognitive science, computer science, and mathematics. So those three departments, we got together and we started a new undergraduate data science major, which is housed here in the Haliciolu Data Science Institute. And it's called that because this is Taner Haliciolu. He donated $75 million to start the institute. So Taner actually is a lecturer in computer science. So if you take computer science classes, he teaches a couple of them, I think. He was Facebook's first employee, so he ended up making a fair amount of money. And he did his undergraduate here, worked at Facebook, hit the startup lottery, worked for Blizzard helping make video games for a while, and then came back to UCSD as a lecturer and teaches a couple of computer science classes. And he donated $75 million to start this institute. And this is a hot topic right now. So this is the classic article from Harvard Business Review, written by Thomas Davenport and DJ Patel. DJ Patel, also a math undergrad alumnus from UCSD, went on to become the chief data scientist for the United States under Obama, back when the country had stuff like that. And they wrote this article in 2012 that laid the foundations for this idea of data science being an independent research field. And the article title, and this really did launch this whole thing, is Data Scientist, the Sexiest Job of the 21st Century. And in Harvard Business Review, that's all you need is this, and then like everybody will start doing that thing. The problem with data science, and it's a legitimate concern, is this. These are the, like, you know, a thing becomes popular and then it's very popular for news outlets to then write things contrary to popular opinion because that gets them clicks. The contrary popular opinion is data science is not science. And okay, well, that's actually like maybe a valid thing. The first computer science department in the United States, in the world, was at Purdue University in 1959. In the lead up to starting that computer science department, people were saying computer science is not a science. We already have math and logic, and we already have electrical engineering. Computers are just math and logic executed in electrical circuits. Why do we need an entirely independent computer science field? It's not its own thing. And of course, anybody computer science major here? A couple of you. It is, you know, I hear a pretty popular major on this campus and at other universities. That's the joke. All right. Fell flat. I'll just run with this. All right. So it has become a huge thing. But it wasn't known that computers were in and of themselves an interesting topic of study, really until people began to figure out the ways in which computers themselves were also interesting uniquely. To put that another way, computers are a tool that we use to do science. How could they themselves be an interesting thing to study? That is paralleled right now to data science isn't science. Data is just a thing. It's numbers that we use to do science with. How could that possibly be an independent field of study? So in starting the institute here at UCSD and in starting the major, which is easily the largest data science major in the country right now, like in the first 20 weeks of the major being in existence. Anybody a data science major? Probably a couple of you. Oh, wow. All right, this is good. All right. There's about 400 data science majors already on campus. And they're expecting 800 or so by this coming fall. So after 1 year, they're expecting 800 data science majors. It's far and away the largest data science. What is happening? So the tie-in between data science and cognitive science is actually an interesting historical thing that began partly here at UCSD. So how did I get into data science? So this is actually a paper from 6 years ago already. Wow. All right. 6 years ago that my wife and I wrote, which was a like data science and neuroscience. This is before data science was really a term. I didn't know I was doing data science. I accidentally data scienced. But my wife and I were working on this project that was started out of frustration that I had during my PhD. So I did my PhD in neuroscience. And as a PhD student, and if you do research as an undergraduate, what your job is in those first years in a research lab is to read peer-reviewed scientific papers, which are very boring and dry things that are written and published by other scientists from all around the world. And unfortunately, neuroscience, I mean, fortunate and unfortunate, is a very popular field. So I already mentioned the annual conference is 35,000 people. And there are 10 to 20,000 scientific neuroscience alone, just neuroscience publications published every month. And there's about 3 to 5 million already been published. So you, as a researcher, if you want to become a scientist in this domain, you have a backlog of catching up to do that's approximately 3 million papers to read. So it'll take you a while. What are we supposed to do with this? Like, how are we supposed to get anything out of that much information? And so what my wife and I had done was started by just saying, well, what ideas are related to each other? So this is fun because I'm one of the first, so I can say this over and over again, and then by the time all the other professors come, you're going to get bored of hearing it. Wernicke's and Broca's areas. All right, so Wernicke's and Broca's areas. How do we have confidence that those are the parts of the brain related to speech and language? Because there's 100,000 papers that people have published linking them. So if somebody writes a paper, and it's 5 to 10,000 word scientific paper, and you can say in that paper, they use the phrases speech and language and Broca's and Wernicke's areas together in that paper a lot. Those words appear together a lot in this paper. And in fact, those phrases appear in a lot of papers together, right? To give you an intuition for what that means, there's not a lot of peer-reviewed neuroscience papers that mention, like, I don't know, Beyonce and the moon landing. Those phrases don't appear together in a lot of papers, so those probably aren't related. whereas speech and language and Broca's and Wernicke's area appear in a lot of papers together. So we can use algorithms. We can take those 3 million papers and take a bunch of different neuroscience-related terms, brain region names like Broca's area or inferior frontal gyrus or hippocampus or striatum. These are all things you're going to have to learn. Good luck. And neurotransmitters like serotonin or acetylcholine or dopamine or whatever, or cognitive or psychiatric dysfunction. So you can look at something like migraines or anxiety or whatever. You can take all of these different terms and say, how many papers across 3 million papers do they appear together in? And maybe 1% of papers talk about these things together. That would be a lot, but like you could say 1% of papers. You can quantify the likelihood that ideas are related. And this is like Facebook's social network graph, right? It's just saying, Jamie and I are friends on Facebook, and Jenny and I are friends on Facebook. Maybe Jamie and Jenny should be friends on Facebook. And so what we did was we built up this graph, but instead of people's probability of being related and friends together, we say, what is the probability of different ideas in the literature being related together? And once we have that, we can then try and find missing connections, like who should be friends on Facebook but aren't friends on Facebook. So serotonin, which is a neurotransmitter, this is an example from the paper, is apparently very strongly related to migraines. There's 3,000 papers that talk about migraines and this neurotransmitter of serotonin. And apparently that is because serotonin, which a lot of people may know as from selective serotonin reuptake inhibitors or a common antidepressant, are those SSRIs, those selective serotonin reuptake inhibitors, are also apparently effective in some cases in treating migraines. So there's a lot of papers that talk about migraines and serotonin. And there's also about 5,000 papers that talk about serotonin in this brain region called the striatum. But there's only 16 across 3 million that talk about migraines and this brain region. Maybe we're missing a connection here. Maybe migraines, we should be looking at the striatum, this part of the brain, in order to understand something about migraines. We can use the data from these papers that we have algorithmically scraped to try and find new hypotheses that we can then study. So this is a data scientific approach. Using the huge amounts of, we would say, unstructured data, just data that are sitting out there somewhere, bring them together, quantify them, and use that to do something. That is sort of the essence of data science. And I took a brief, like 1 to 2 year aside in my career to work as a data scientist back in 2011 for Uber. Don't hold it against me. And when I was working at Uber, the idea was, how do we use data in order to make a service better? So what became very clear very early on is that if you open up the app, and if you've ever used a ride-sharing service, Uber, Lyft, whatever, you open up the app and it tells you approximately how far away the nearest driver is. And if you open up the app and it says the nearest driver is 20 minutes away, or 30 minutes away, or 40 minutes away, you're just going to be like, ugh. And you close the app, right? Like that's the face everybody makes. They go, ugh. Right? Whatever that thing is that we do. They then close the app. If it is 8 minutes away, you're like, okay, that's all right. So we can plot the probability, this is the one trivial example, plot the probability of a person converting from opening the app to taking a ride, like actually successfully using the service, based as a function of what is the estimated time of arrival of the nearest car. And what you get is a curve that looks like this, where if it's 20 minutes away, you are very unlikely to actually end up taking that trip. If it's 1 minute away, you are very unlikely to actually end up taking that trip. The reason for that, we think, or we thought, I haven't been there in a long time, was the like too convenient factor of like you're in your apartment getting ready, and you're like, okay, I better call an Uber, and you're like, 1 minute away, I'm totally not ready yet. I'll just close it, and I'll try again later. So there's this like sweet spot around like 6 to 8 minutes. So you can plot your data, and you discover this kind of thing. And then your job as a data scientist or a statistician or whatever is to write a set of equations or an equation that describes this function. That's a function, right? So you have to say, okay, how can I best model these data mathematically? And then once you can do that, you can then start to do some pretty wild stuff. So here's an example showing, at the time, the probability of people actually completing a trip as a function of the ETA for 2 different years, 2013 and 2014, within the same city. And what happens is, every year that Uber was in existence, this curve shifts back by about 1 minute. People get overall about 1 minute less patient. The longer the service exists, the more people begin to expect of that service. So this is like a way that companies can use their data that they are tracking and storing in order to try and come to some actionable business conclusions. That's like very, very basic mathematical modeling type stuff that companies will do. But what is the data science? What makes something data science versus just math? This is my data science class. It's big. There's a lot of people. What makes data science different, this is what I teach in these data science classes, is integrating a huge number of data sets from different sources. So now, let's imagine you are a data scientist at a place like Facebook, which this example is now more timely now that I'm saying it, I realize. You are a data scientist at a company like Facebook, and your job is to try and figure out what is the probability that someone will click an ad that they see. So you've got, what, like 2 billion users or something across the world, and your job as a data scientist is to help Facebook make money by getting people to click on ads. What information do you have to make that estimation as to whether or not somebody will click an ad? So, I mean, wait, hold on. Should I like talk about Snapchat or something? Like, I'm old, so I use Facebook. Is Facebook something people still use? I don't even know anymore. Genuinely, I do not know. But let's presume you understand what Facebook is still. So Facebook is the social network. No, I'm just kidding. All right. So what you have access to as a data scientist might be information about a user's demographics. So their self-reported gender, their self-reported birthday, where they live, maybe where they grew up, their hometown, what schools they've attended, where they have worked. These are all things that we freely give to Facebook. All right, it's like, here's all my stuff. Please mine everything you can about me. And then you upload, oh, this is like risky. Let's see if I can do this. I don't know if I should do this actually in front of a crowd. I'm going to show you my Facebook page. Let's see what happens. Okay, so I am going to, I'm like very nervous about this now. All right, so I am going to, sexiest, there it is. Let's look at that. Okay, so I'm going to right click on this and say inspect. Oh, that's not very interesting. It just says one person. All right, let's go to another one. Oh, this is like very, I shouldn't do this. All right, that's my adorable son playing baseball. All right, inspect. That's his first run ever, by the way. He was very proud. Okay, so check it out. Look. It says, may contain one person smiling, playing a sport, baseball, basketball court, and outdoor. If you post a picture on Facebook and right-click on it and do that inspect, it will tell you what it thinks is in that image. So what's happening under the hood is every photo that you upload to Facebook is going through computer vision algorithms that will try and extract what information is in that picture to the best of the algorithm's knowledge. And it also contains metadata about that image. I'm going to take this off now in case there's like anything else weird. All right, let's go back to this. All right, so it contains that metadata. So every photo you upload, it'll say when and where you took the photo. It tries to deduce what is in that image, what time of year, right, you posted it. It knows your demographic information that you've reported. It knows, excuse me, it knows your social network. And that social network isn't just, are you friends with that person and that person and that person? They know how strong of a friend relationship do you have and in which direction. So if you go to Facebook and you're scrolling through your Facebook timeline and you don't click on anything in your timeline, but you're scrolling and you pause and you're like, oh, they look pretty good. And then you continue scrolling, they record that dwell time. How many seconds did you spend looking at that image as you're scrolling through your feed? Whose image were you looking at? All of that stuff, even if you never click on anything, is being recorded. So they can estimate pretty well your interest in another person, even if you never click on their profile or click on their photos or do anything, just by how long you like dwell on their image as you're scrolling through the feed. They also have information, and that's not equally directionable. Like that's not an equal weighting. Like you are probably dwelling on other people's images more than they're dwelling on yours. So that's a weighted graph, we say. So what's your interaction strength with other people that are in your friends? It has information about the text that you post when you write Facebook status updates. Right? And it can do text mining on that to figure out what the general sentiment of the text is. Is it a positive or negative thing? What's the word complexity? How many words is it? What language do you do it in? Do you mix languages? It also knows information about hyperlinks that you post. So if I post a link to the New York Times in my Facebook, I am more likely to then post in the future a link to the Washington Post than I am to like Fox News or something, right? Because you can, the HTTP URL internet graph, that's a graph too that has connections. So now you have access as a data scientist to textual information, demographic information, pictures that you can do vision algorithm recognition stuff on, graphs, which are the graphs to the link you post, as well as your social network graph. How do you take graph data, text data, image data, time and space of where and when you posted it, and come to one number of, is that person going to click on an ad or not? That is the crazy complexity. That is the interesting part. That is the art and the beauty and the danger of data science, is being able to take tons of different data sets from different sources and try and distill some knowledge about a person based on those data. So the data science has already been pretty successful here. We've had a number of guest lecturers come through the Data Science Institute. We're starting a distinguished lecturer series more formally. But lots of practicing data scientists from Uber, Netflix, Pandora, Twitter, DJ Patel, who is Obama's chief data scientist, City of San Diego, Slack. We've had tons of people come through. What is data science, though? This is what we're still struggling with. We're getting a little bit closer. But this is from Jeff Hammerbacher, the guy that co-coined the phrase data science. He co-founded Cloudera, which is a sort of popular tech company. And he says, the best minds of my generation are thinking about how to make people click ads, and that sucks. So data science, the state of the sort of field in the 2011 to 2014 stage was just this. Most data scientists were trying to just figure out how to get people to click on ads. And there's been a big push to what more can we do with this sort of power that we are uncovering. So we try to define what data science is here at UCSD. This is a UCSD specific definition. It's the study of how the quantification of, this is very dry and technical, how the quantification of observable phenomena can lead to human understanding of the processes giving rise to those phenomena. What the hell does that mean? We'll get to in a minute. Or even the ability to predict future outcomes absent any kind of human understanding. So we can write algorithms that accurately predict the future for us without any understanding of how those algorithms are doing what they're doing. And why is it that certain phenomena require more or less data to lead to human understanding and or prediction accuracy? So what does that mean? Automatic machine translation has been the bane of linguists and cognitive scientists for 70 years. It's incredibly difficult to do. And let's see if I've got an app here. All right. Now I can open up a trivial app. It's a free download thing, right? And I can try and say, let's see if this works. All right. Somebody give me something to say. What's a banana? Okay. Well, let's get a little bit more complicated. I would like to buy a banana. Was that close? Okay, all right. So I can do that to any language. Does anybody in here speak, let's see, Italian? No? How about Hindi? All right.
Hindi.
Let's do it. I would like to buy a banana.
मैं एक केला खरीदना चाहते हैं.
Yeah? Pretty close. Close enough that if I need to go to a country and talk to somebody, it'll be good enough. All I need is this and an internet connection, and I can talk to anybody in the world. Not quite in real time, but pretty dang close. Good enough. That was like magic 15 years ago, right? If somebody had that technology when you were kids, that would have been mind-boggling. That was unfathomable. Why can we do that good enough now? That system doesn't know anything about grammar or syntax or prosody or phonemes. nothing about that kind of stuff, which is what linguists for a long time thought we would need in order to get computers to do machine translation. We thought, as a field, that if we wanted computers to do automated translation for us between languages, we would have to hard code into those computers the ideas of syntax, all of the rules, the universal grammars, whether or not they exist, all of these things that we have learned about speech and language. And then Google came along and said, actually, if you just have enough data that has automatically been translated by people across web pages, we can do it just using the data. We don't know anything. We code nothing about grammar or prosody or any of that kind of stuff. It just does it. It figures it out with enough data. How much data do you need to get that to work? We don't know. These are totally open questions. Why does that work? There's a lot of weird things that happen when you have a ton of data that break what should we think are statistical rules that should be pretty constant. That once you have enough data, you can do totally ridiculous things that shouldn't work statistically but suddenly do. And I'm just leaving all that very vague because that's what we teach an entire major for. All right. So what is the point of data analysis? Prediction, classification, knowledge discovery, and honestly and frankly, doing useful shit. Sometimes we can do really useful things like automatically translate whatever I say, would I like to buy a banana, into any language that is ever spoken in the world right now to a good enough extent. That's useful. It doesn't matter how it works. So humanity has been dying of diseases for the entirety of evolutionary history, right? And somebody came along and accidentally discovered that there's some moldy kinds of bread that if we eat that, that'll stop us from dying of certain diseases. Well before any understanding that that is called penicillin and what germ theory is, people just kind of knew that that stuff worked. People don't care about germ theory if they're not dying, right? So you can do very useful things. That's kind of the history of humanity, is accidentally discovering cool stuff to do without knowing how any of it works, right? That is the cool part of doing data science. Now, the issue there is, can we learn from our past mistakes in order to stave off any future disasters before they start through data science, right? Data science is a very powerful tool that can be used for incredible amounts of good, but also incredible amounts of maybe not so good. And can we learn something from that? So what do I mean by prediction? Does everybody know what, you hear about I'm in Venus in retrograde or whatever, I'm a Sagittarius under that, whatever, right? What is your planet being in retrograde mean? What does that mean in the astrology thing? That's not a science, by the way, just for clarity, astrology. But planets do move in retrograde. What does that mean? If you actually look in the night sky and you say, I'm going to plot every day where all of the brightest points in the night sky are over the course of a year. People did this millennia ago. Namely, the Greeks formalized it. And they noticed that a handful of those points of light in the night sky didn't stay relatively fixed. They moved faster and every now and then would loop back for a couple weeks before moving back forward. They called those handful of weird moving things the wanderers, or the planetos, which is where we get the word planets. And they just said, that's a weird thing that happens. Why does that happen? So this is the beginning of science. Step one of the scientific method is observation. I have observed a weird thing that happens in the world. Step two is, why does that happen? And then you come up with hypotheses. And you try and understand, you build models for that. And when I say models, in modern era, we usually mean mathematical models. We have a set of equations. Why do planets move that way? Because of Newton's laws of mechanics, F equals ma, right? But before we had that, people built physical models. So, quick little video aside.
Appear to temporarily change the direction of their orbit. They don't change direction, it just looks that way from Earth. It's an illusion that unfolds over a matter of weeks or months. In this image, Mars was photographed every 5 to 7 days between October 2011 and July 2012. Once all the photos were combined by aligning the stars in the background, it appears as though Mars looped back on itself before continuing on its orbit. A retrograde illusion like this happens when we lap an outer planet like we do with Mars every 2 years, or when an inner planet laps Earth like Mercury does every 4 months or so. But for both Mercury and Venus, the illusion is hard to actually capture, since they're located on Earth's day side, not on our night side. When those planets are visible, it's only right around sunset and sunrise. But assuming you could see it, here's a diagram of how the Mercury retrograde illusion would work. This line shows our view of Mercury against the background stars. As Mercury passes us by, our line of sight shifts so that for about 3 weeks, Mercury will appear to loop back on itself when viewed from Earth. It's simply a function of two objects orbiting in the same direction at different speeds. If you stood on Mercury, you would see Earth make an apparent loop too.
That is how it actually works. For thousands of years, this was the model that people had for how it worked. This is the Ptolemaic model that assumed Earth is at the center. This is the geocentric solar system, I guess it's geosystem, right? This is the geocentric model. And in order for the geocentric model to work, to account for this apparent retrograde motion, all of the other planets have to move around like this. This model works. It is an accurate model in the sense that it predicts the future motion of the planets in our night sky. It's a great model. But it's also a garbage model, because it's wrong.
Earth is stationary and at the center of the solar system. In the 2nd century, Ptolemy devised a complicated system of loops and orbits within orbits to account for the retrograde motion of planets. That model was accepted for 1,500 years because it seemed to fit the observations, even though it was completely wrong. Once Copernicus showed that all the planets, including Earth, move around the sun, then retrograde motion was easily explained as an illusion. So if there's any life lessons to learn from Mercury retrograde.
So you're going to just have to wonder what those life lessons are. All right. So this leads to a famous paper written in 1976 in statistics, in which there is a phrase: all models are wrong, but the scientists cannot obtain a correct one by excessive elaboration. On the contrary, following William of Occam, which is Occam's razor, which is the simplest answer is often the correct one. Following William of Occam, he should seek an economical description of natural phenomena. I think it's funny, it's 1976, all scientists were he's. Anyway, just as the ability to devise simple but evocative models is a signature of the great scientist, so over-elaboration and over-parameterization is often the mark of mediocrity. All right, that's a academic beatdown. What he's saying and what has been distilled out of this is this idea that all models are wrong, but some models are useful. So, is anybody taking basic physics courses here? You start with classical mechanics, and then you take E&M, maybe, right? And then after E&M, you'll move on to eventually like quantum. And I'm sorry if you do. What happens in each of these classes is you'll take classical mechanics, and you're like, holy crap, I am a god. I can predict where that marble's going to be 10 minutes from now, right? Like, it's silly contrived problems, but it feels really good when like the math works out. But then you'll take E&M, electricity and magnetism, and then they'll be like, actually all the classical mechanics stuff is kind of wrong. It's good enough. It's a first approximation. Here's how it really is, and suddenly you've got like nested differential equations that don't make sense. And then you take quantum mechanics, and they're like, actually everything is wrong and we know nothing. And here's really hard math to describe that we know nothing. Every level that you go, you find out that the models that you are using, mathematical or physical, are wrong or at least incomplete. It's more complicated than that. And so the trick of data science is trying to figure out the right balance between I have a huge amount of data that lets me predict something that I need to predict. I don't care why it works, it just works. And balancing that with, is this the right model that makes sense? Is it real? Does it reflect something real? Or is it a spurious correlation? So, how are data science and cognitive science related? Why is cognitive science one of the 3 departments? So, one is, I love this. This is, if you ever code something that feels like a hack but works, just remember that a CPU is literally a rock that we tricked into thinking. Right? So, right, these are just like, silicon computers are just rocks that we've somehow managed to trick into doing thinking for us. And as a cognitive scientist, I go, ha ha ha, yeah, but is it really thinking? What does thinking mean? right? So the actual history of data science is really just like a historical kind of cool accident / confluence of a number of ideas in math with a huge amount of data, with neural networks, which were totally passé and like boring and uninteresting for decades, suddenly working when you have enough data. And what is an artificial neural network, and how does it play a role in data science and cognitive science? So this is a neuron. Actually, these are two neurons, and a neuron has a cell body, and it has these little dendrites, little tree-like structures, dendrites, and it has this long, we say process. It has this long thing called an axon that almost connects it to another neuron. It doesn't actually physically touch. There's a tiny little space called the synapse, or if you're British, synapse. This is how neurons, your 86 billion or so neurons, are wired. Not technically, it's more complicated than that, but we're, first years, we can run with this. All right, they receive a signal, and they trigger when that signal is big enough. So neurons communicate through what are called all or nothing action potentials. They receive an input, a charge builds up across the membrane. Once that charge, that voltage hits a threshold, it sends a big spike of activity that lasts like 1 to 2 milliseconds, and that releases neurotransmitter onto the next neuron. That led people in the 1960s-ish, 70s, to build what are called mathematical neurons, which are the components of an artificial neural network, which, if you've heard of deep learning, that's just a whole bunch of these things wired up in many layers. And a mathematical neuron is what makes up an artificial neural network. And that's an abstraction that is taking sort of a little cue from biology and saying, it's pretty cool that neurons do this. What if we can simplify that mathematically and say, we're going to have a thing, and it receives inputs x1, x2, x3, and so on. And if those inputs then sum to a high enough number, it's going to then do a thing. And that's a mathematical neuron. It's a simplification of real biological neurons. And people began to discover that if you hook up a bunch of these mathematical neurons in simulation, interesting things begin to happen. And that was the convergence between cognitive science and computer science. Largely starting here, at least UCSD was a major player in the 1960s and 70s in this domain, which is where cognitive science as a department kind of came from, was groups of psychologists and neuroscientists and computer scientists who were working on AI and neural networks kind of coming together and saying, hey, we're all interested in the general same idea of intelligence. Let's come together and try and figure out what this cognition thing is. And then there's been one hell of a divergence in the last decade or so. So neural networks were passé. They were like, there's something called the AI winter, which is a period of about 30 years where artificial intelligence research just experienced this huge decline because people had these amazing ideas, but none of it was working very well. It just wasn't paying off until you had enough data. And then suddenly things started to explode and work really well. So you have now headlines like this from the past, decade or so. Google AI defeats world's Go champion in a gripping man versus machine film. The AI revolution, why you need to learn about deep learning. Google's artificial intelligence can actually help the environment. A computer's newfound intuition beats the world poker champion. AI can solve the world's biggest problems, says a Google brain engineer. Like once you work for Google, you don't have a self-identity anymore. You just become a Google brain engineer or something. So let's go back to this. Yeah, but is it really thinking? Why does this matter? So this is a joke. This is not a real thing. There's a neuroscientist named Mark Humphreys that wrote this thing, which is, so people, if you don't know, we had computers that could beat the world's chess experts back in like the 90s. But Go, anybody ever played Go or know what it is? It's a pretty complicated game. I mean, the rules are very simple, but the number of degrees of freedom, the number of moves possible are immense. And Go champions, the world's best Go players, when you ask them, you say, how is it that you are so good? They often will sort of default and say something along the lines of, there's an intuition for this complicated game board that you build up over the years. This was thought to be a game that was just impossible for computers to win because computers do not have that kind of intuition. And Google, 2 years ago, built a system that finally started regularly beating the world's best Go players. And this is kind of a joke. So in 2040, this is an artificial fake history of the future, DeepMind, which is one of Google's sort of little AI arms, published Alpha Cluedo. Does anybody know the game Clue? Right? It's like a game where you have to try and figure out who murdered who in which room, right? It's like Colonel Mustard in the observatory with a wrench or something, right? So in 2040, Google publishes Alpha Cluedo, released as Alpha Clue in the North American market. Despite running on 100,000 GPUs, it still loses 0 to 50 to its human opponent. And an investigation reveals that the human opponent simply opened the envelope and read the answer. So humans, we're still good at cheating. Computers have a hard time with that sometimes. Oh, anyway, so what is it that these systems are doing? And what is it that allows like huge amounts of data to allows computers to leverage huge amounts of data in order to do what appear to be somewhat phenomenal or even magical, unknowable things? So we have to step back and talk about what is cognitive science. And this is a contentious question. In order to understand why computers can do what they do now, we also have to try and figure out what is cognitive science. So this is my definition. I'm one of the first guest lecturers, so I get to poison all of your minds with my thoughts. All right, so it's a study of intelligences, both natural and artificial. What does that include? Well, communication is critical for cognition. So is computation and reasoning and memory and planning and decision making. Right? These are all critical elements of cognition. Right? I can plan for the future. I know that in order to get my son to his baseball game tonight at 5, I have to leave here at 4 o'clock in order to beat traffic and pick up my son and get him in his gear. That's planning. These are things that we all do. You make your schedules for classes. You can plan months ahead of time. You are going to college right now to get a degree to plan years in the future that I want to do this thing and get a job that pays me so that I don't have to keep eating ramen for the rest of my life, right? This is all, well, I mean, you may not be thinking about it that clearly, but that's the idea. Like, why are you here? Right? We can plan in the future, and that's an amazingly complicated thing. Like, how does the brain do that? Well, we don't know. But we can start by saying what has cognition and what does not have cognition. So humans are like the gold standard. We generally agree that humans have cognition. Do babies have cognition? These are my 2 kids. So these are them when they're babies. And at this stage, arguably not very cognitive, but this implies that cognition is not an all or nothing thing. It's not a 0 or 1. There's maybe a spectrum of cognition, right? As babies, they're not very cognitive. It's not like my baby daughter, when she's screaming at me at 2 in the morning, when she's a newborn, is like, really, Dad, I'm having an existential crisis right now, and I'm really worried about, like, my future, right? That's not what her concern is. Her concern is, like, I've got poop and I need to eat, right? That's it. But it's arguably still cognitive. Now, at this point, by the time this is her at 2, she is very cognitive and has very strong opinions about the world and clearly lets me know them as best she can, right? So something happens along this developmental trajectory in which cognition begins to emerge. And so you will hear from people in this class that do cognitive science in development, trying to understand how does cognition develop in children? What are the different stages of a cognitive development, and so on. So that is one branch of cognitive science. Now, what about non-human primates? So you may hear from Professor Rossano here this quarter. He studies non-human primates. So these are animals that we share a relatively more recent evolutionary ancestor. Our brains look largely similar in their organization. They have the same brain regions largely that we do, and they can do some pretty cool stuff. So that's one, using a tool to break open a nut and teaching another animal how to do it, and then that animal will go and teach other animals to do it, and so on. There is something pretty amazing. You think about an ant. What can an ant do? What information does an ant carry in its life? Everything learns. Every animal learns a little bit. But it cannot carry anything new that it has learned across generations. The ability to take something that we have learned in our own lifetimes, distill out something useful and informative from that, and then share that information to future generations was a huge evolutionary leap. The ability to no longer be constrained, our memories are no longer constrained as a species to our own lifetimes. We can now share information across lifetimes that reduces the chance of my offspring dying, because I can say, don't eat that berry, that's a poisonous berry, and I can then share that information with them, and they are more likely to survive. That fact that we can do that is remarkable. Okay, what about other mammals? This is my puppy Ada. She's pretty smart. She knows a lot of things. But she also is still a mammal and has a very similar general brain structure. I can tell her to sit and roll over and play. She seems to get worried about stuff. She has like some idea of future planning. Like if I walk to the certain part of the house where the leash is, she knows what's about to happen and gets very excited, right? So she's anticipating the future. So animals do this kind of stuff. They have, you know, some crude, at least, understanding of future events. But what about something like a crow? Now, this is a bird. Birds are dumb. I don't like birds. But they've got tiny little brains, and they don't even look like our brains. We have 6 layers of cells in our neocortex, which is the outside of our brain. They only have like 2 or 3. Their brains look very different, but damn, some crows are really smart. So that wants that treat. It's in a beaker filled with water, but it can't get it. So it's basically having the eureka moment that Archimedes had in the bathtub when he overflowed the bathtub, right, and learned about displacement. The bird is learning that if it puts these things in there, it'll raise the water level and be able to get the treat. And more than that, like corvid intelligence in general is like crazy. These are really smart birds. There's a group, this is a paper published a couple years ago, there's a group of crows in the UK that lives in trees right around, you know, in civilized parts of the world, they don't have stop signs, they have roundabouts to keep traffic moving, right? And cars flow constantly across these roundabouts. And the trees on this roundabout in which the crows live, or at least hang out, have a bunch of nuts. But the nuts are in very hard shells that they cannot open. So the crows drop the nuts into the street and wait for the cars to run over them to break open the nuts. But the problem is there's constantly traffic. So then the crows all wait for a pedestrian to then cross the traffic, at which point all the cars stop, and then they flock down, grab all the nuts, and fly away. So the crows are planning ahead. In a group, they have learned from each other that if they want these nuts, they can drop them in the street and the cars will run over them, but they have to wait for the person to cross the street in order to block all the cars. And so this is something that a group of crows transgenerationally has learned in the UK at this one place. And it looks like they're like teaching other crows in different parts of the city how to do this. So these things don't even have brains that look like ours, but they're still able to do some what appears to be learning and teaching. And tool use. But we're the tools. All right. And then you have something like an octopus. Octopuses are freaking amazing. They don't even really have brains per se. They have a collection of neurons or ganglia that are spread across the different like body parts. Like each tentacle has one, for example. They don't have anything that looks like a centralized nervous system. So they don't even have a brain in the same way that we do. But they're also incredibly scary smart. So this is an octopus. This is a group that do this in, I think it's like the Caribbean. And they want to go feed. And in the parts of the water that are very rich in like broken down fish and detritus that are easy for them to eat and get, the reason that there's lots of broken down fish and detritus in the water is because sharks are eating all of these damn fish. And they miss all the pieces, and those sink to the floor. And the octopuses want to eat those. The problem being, if they go there, there's also a lot of sharks there. And so what happens is, before the octopus or octopi, groups of octopi, all right, I got it right. What they do is they'll find these empty coconut husks, and they'll just sort of walk along the seafloor with these empty coconut husks. When the researchers first saw this, they're like, what is going on? Why are they doing this? But what happens is, if they're threatened by the sharks, they will then enclose themselves and use their suckers to hold the 2 shells tight around itself and encase itself in armor. So this octopus is going, I'm hungry. I'm going to go over there, but there's some sharks over there. Let me grab some armor first, and then I'll go into that water. Uh-oh, shark time. Hide. That appears to be planning. Right? Like, it is anticipating the future and it is behaving accordingly in order to like protect itself. What is happening? Because I don't even have brains. Like, how does this work? Okay, slime molds. Let's talk about slime molds. These are pseudo-unicellular things. This is like literally just like crap that you like power wash off your, like gross. I'm going to use some like, spray and kill this stuff, right? These are unicellular things. But they become pseudo-unicellular, meaning they're not truly multicellular like we are, but they'll grow into these like pseudo-multicellular strands when there are food sources. And so they sort of grow out in these sort of tendrils. And this is what it looks like. This is rapidly sped up, but this is what their growth looks like. And they grow out in this manner to find food sources. So here's an experiment done a number of years ago where they seeded these slime molds in a petri dish that had this funky shape and had all these little dots of food. And the slime mold grows in all directions until it hits food, and then it pairs back into these tendrils. And now it's found, like, it's connected all of the food sources to pass the nutrients around. So what's funny about this experiment is this outline is the outline of the greater Tokyo area. And each one of these dots are train stations, represent train stations where they seeded the food source. This is the actual greater Tokyo area train network. This is the mold network that the molds found. This is actually more efficient routing between train stations than this. This is the human-designed train network. And the mold found a more efficient routing than the humans did. So I kid you not, there are urban planners in the world who are growing mold in order to find the best way to route different neighborhoods using trains and roads and things like that. So these are unicellular. They have no brain whatsoever. They have nothing. They're a cell that grow into these pseudo multicellular things that are useful. That's not cognitive, but maybe it is, maybe it isn't, right? I don't know. But it is still useful. What about Watson? Right? This is the computer program that won Jeopardy. It beat Ken Jennings, who is like the all-time winningest Jeopardy guy. He won like, what is it, like 30, 70, 80, what is it? Anybody know how many he won? It was like 80 or 75 in a row, games of Jeopardy. He won over $1 million in Jeopardy total. So this guy is incredibly good at Jeopardy. And he got his butt kicked by IBM's Watson. Watson is IBM's cognitive computing. Now it's their division. But look at this. These are the kinds of questions that the computer could answer. So first of all, Jeopardy's funky in that you have to phrase your question in the form of an answer, or your answer in the form of a question, I mean, right? This is like, look at this. William Wilkinson's An Account of the Principalities of Wallachia and Moldavia inspired this author's most famous novel. How are we parsing that? So we say English is a non-tonal language. What does that mean? Does anybody know what that means? Does anybody speak a tonal language? If you speak Chinese, you speak a tonal language. What does it mean, tonal? Right. So in tonal languages, the tone, intensity, and pitch of what the word sounds like has meaning. English is said to not be tonal. So if I tell my wife, that dress looks awesome tonight, or I say, that dress looks awesome tonight, or that dress looks awesome, or okay, awesome, right? Those are all different ways of saying the same thing that do carry different meaning, right? So to say that English is non-tonal is a little bit trivializing. English is complicatedly tonal. But our language is incredibly complicated in many ways. So when I read this question, I say William Wilkinson's An Account of the... Notice what happens there. I don't say William Wilkinson's An Account. I say William Wilkinson's An Account. I pause a little bit longer, and that pause indicates that there's some sort of clausal phrase being separated off. So I say William Wilkinson's An Account of the Principalities of Wallachia and Moldavia, and I pause again extra. We just do this naturally. Right? This is an accidental thing that we learn somewhere to pick up and read from each other. And somehow you have this system, Watson, that is able to parse these kinds of questions and piece apart the answer. So this is Ken Jennings losing on Final Jeopardy. He says, I, for one, welcome our new computer overlords. Can computers be cognitive? Or are they just cheating? Are we just coding in the answers? This is like a fundamental question, really. I think we're just cheating also. We've just been cheating longer over evolution, so it looks like we're super cognitive. What's the link between cognitive science, and data science. What is cognitive? What isn't? So I'm going to go back now to talk in the last like 10 minutes or so about my research to try and tie this all together. So this is Nate Silver, who wrote The Signal and the Noise, sort of made data science sexy, I guess is the phrase, right? Predicting elections. He was initially a sports analyst. So I'm going to play for you something. It's a 7-word sentence. I've taken the sentence and I've digitally altered it to remove useful parts of information. So it's going to be both difficult to hear, which is the intention, and also very annoying, which is not intentional but kind of funny. So listen, and I apologize, sort of. She writes to her brother every day. Okay, so if I run an actual experiment and have people write down what they heard, on average, people get like 2 to 3 words correct. They'll hear. Okay, now I'm going to play the true sentence unfiltered.
She writes to her brother every day.
Anybody get it the first time? Pretty close, yeah. A couple people on average will, and like 1% or so usually get it. Now, I'm going to play the original filtered version for you again.
She writes to her brother every day.
So you hear it now, right? You can't unhear it. Has anybody heard me do this presentation before? Did you hear it the first time? No? Did you hear it the first time after hearing me do this? Yeah, so you kind of remembered, right? So, thank you. You will remember 6 months from now that she writes to her brother every day. You will hear it again. Like, that's now in your brain, and you are going to hear it. What is happening? So, what is hearing? When I speak, what is happening is my vocal cords are vibrating, and that is pushing air. And this air, which is invisible to all of you, is vibrating. And then that air vibrates your eardrums, which causes little neurons in your ear to physically open up ion channels to allow electrical charge to rush in, which then sends a signal into the primary auditory cortex 17/1000ths of a second after that sound hits your ear. So in 17 milliseconds, you go from vibrating eardrum to I heard a thing consciously. Somewhere in that 17 milliseconds, your brain is literally modifying the activity in your primary auditory cortex, which is the part of the brain where the sound comes in, to modify it using your memory. So you have an anticipation based upon the unfiltered sentence that you just heard, and that anticipation signal is colliding in your brain with the actual signal, and it's modifying the actual signal to try and amplify the thing that you expect to hear. This is a crazy thing that happens in our brain. We are constantly building up expectations of our experience that we then experience just as strongly oftentimes as the true signals that we get in. This is why we are susceptible to illusions. This is why there is something called pareidolia, which is where we see faces in things where there may not be faces. It's because we are building up expectations of the world around us. From an evolutionary perspective, this makes a ton of sense. It is better for us to hallucinate a tiger in the grass and be wrong and say there is no actual tiger and be a little bit like on edge that there might be, versus under-expecting and being like, nah, I don't see anything. There's probably nothing. And then die, right? So this expectation thing where we kind of build up a reality a little bit that may not be entirely real as we go along is a very useful thing for us to do. And it allows us to fill in missing information when we need to find. How does the brain do that? This I find fascinating. This is just an example. I don't actually study that exact thing, but this sets up the problem. That somehow there's one part of the brain that builds up a representation of the world that collides with the actual input that we receive from our senses in order to build up a representation of the world around us. So how do we study this in neuroscience? It's very hard to do. So we cannot record brain activity from humans. I have until 10:50, is that right? Okay. I timed it right. We cannot record brain activity from humans because apparently you're not allowed to open up their skulls and get in there. I've volunteered. Apparently it's unethical for neurosurgeons to do brain surgery unless you need it. So I can't do that. So instead, we resort to non-invasive brain imaging methods. So the two tools that we frequently use are and you'll hear about these, fMRI, or functional magnetic resonance imaging, which measures oxygen changes in blood in the brain. So when groups of your brain cells are more active, they use up a lot of glucose and energy, and in response, more blood, oxygenated blood, flows to that little brain area to give them back the oxygen that they used up. That is what fMRI measures. If you ever see like a study where they show like, pictures of brains with the little like different colors on them, that is what is being measured. And that's an amazingly powerful technology. Unfortunately, it's not actually measuring brain activity directly. It's an indirect measure, an inference based on oxygenation. And it's very slow. So neurons will send an action potential in about a millisecond or two, which is a fraction of a thousandth of a second. These oxygenation changes occur many seconds after the brain region was active. The other method is the currency by which neurons communicate is electricity. So the other method that we have to actually measure how neurons work is by measuring the electrical output of neurons. But we can't do that because the skull is in the way. And when the neurons in my brain send a bunch of signals, those signals hit the inside of the skull, and like a wave crashing against a rock, just spread out. And so we can use what's called EEG, or electroencephalography. They put these little electrodes on the surface of your head. You can buy them like at home, and they have like the Muse headsets and things that like help you meditate supposedly and stuff like this, right? Those are EEG systems. They're recording electrical activity, but we cannot figure out where it's coming from in the brain because this electrical signal hits the inside of the skull and splashes around. So using fMRI, we can measure precisely where in the brain was active. And using EEG, we can precisely measure when was active, but we can't do both at the same time. So in order to get around this, my lab actually works with people who have electrodes implanted directly in their brains. And these are people who are undergoing surgery for epilepsy. So epilepsy is a disease that causes seizures, and about 3 to 5% of the population has some form of epilepsy. Most of it is very mild, and you'll have what's called absence seizures, which is you kind of space out for a few minutes. But in the most severe cases, you will lose consciousness for many minutes, multiple times a day. Now, thankfully, there are anti-epileptic drugs that treat that very effectively. But for whatever reason, of that 3 to 5% of the population that has epilepsy, a fraction of them who have the very severe form, a fraction of them do not respond to the anti-epileptic drugs. It just doesn't work for whatever reason. So you've got a couple tens of thousands of people every year who choose to undergo a brain surgery wherein they remove a piece of the skull, implant electrodes all throughout one part of the brain to try and figure out exactly where the seizures are coming from. We can't do this non-invasively, so it has to be done by opening up a part of the skull and implanting electrodes in a ton of different parts of the brain. These electrodes record electrical activity coming off of neurons, and then the surgical team can precisely identify, there it is, that's the part of the brain causing the seizures. In order to do that, though, they have to wait for a week or two while the person has these electrodes in their brain for the person to have enough seizures for them to be able to figure it out. And then what they do once they figure it out is they remove all of those electrodes and then remove the part of the brain causing the seizures, put the skull back in, and 90% of them are seizure-free. It's an incredibly successful surgery that has been done for 60 years in very much largely the same manner. Not a whole lot has changed. And during that week or two, so here at UCSD over at Thornton Hospital is where these surgeries are performed. The neurosurgeon her name is Sharona Benheim. She's been doing these here at UCSD now for about 2 or 3 years. And we work with her and her patients. During that week or two, while they're awake with these electrodes in their brain at the epilepsy monitoring unit over at Thornton Hospital, talking to their friends and family, watching TV, playing video games, doing whatever, reading to take their minds off of the awkward, kind of uncomfortable, very difficult and stressful situation. And while they're there in the hospital, we approach them and say, this is a pretty unfortunate situation. We appreciate what's happening. Would you mind, this is an invaluable tool, like you provide us with an invaluable opportunity to study the brain. Would you mind doing our memory studies? So we ask them to play like some memory games, for example. But now we can record exactly what neurons in human brain are doing. So this is what it looks like. If you are squeamish and do not like the sight of blood, now is the time to look away. I have had a person faint on me, not like physically on me, but in a lecture hall. So look away, please, seriously. So that's in the operating room, a video I took. This is what it looks like after the fact. These are two different people that got different kinds of electrodes implanted. These little dots here are the electrodes on the surface of the brain. We've removed the brain digitally. These are actually deep electrodes that penetrate far deep into the brain. So these are on the surface. This patient got electrodes deep into the brain. Okay, you can look back now. All right, so first of all, did you notice the brain pulsing? So even though the brain is only about 2 to 3% of the overall body mass, it gets something like 20% of the output from the heart. So with every heartbeat, it gets so much blood relative to its size that it actually pulses a little bit. And those little numbers on the surface of the brain, there is Dr. Benheim's assistant is standing there holding a clipboard. Actually, it's an iPad now, that has numbers on them. The patient's awake during that part of the surgery. They're lying there like this, and they're electrically stimulating different parts of the brain. So even though I just got done telling you this is the part of the brain that does vision, these are the parts of the brain that do speech, that's not really totally true. This is the E&M part of classical mechanics, right? That's not entirely true. It's different for everybody. Some people have language on the right side of their brain. For whatever reason, some people have language a little bit farther back or a little bit higher up. Everybody's brain is just a little bit different. So in order to make sure that the person doesn't wake up after the surgery when they've removed part of the brain, unable to move or unable to speak, they wake the person back up during the surgery and electrically stimulate parts of the brain to see what fingers or body parts moved when they stimulated to map out that exact person's brain mapping so that they avoid those parts of the brain when they go around to try and pull out the part of the brain causing the seizure. So this, in the last 5 minutes, will be then what is the intersection between data science and neuroscience. We have 3 million peer-reviewed publications that I talked about, and we still know very little about how the brain works. You have people that are studying genes. What is the genetic basis for cognition and brain function? There's 20,000 or so different genes that are expressed across the human brain. There are people that study what parts of the brain do which things, which ones do memory, which ones do attention, speech and language and grammar and movement. There are parts of the brain that express different kinds of cells. There is a group of cells in the brain that are excitatory, meaning if this neuron fires, they excite the downstream neurons to make them more likely to fire. There's also inhibitory neurons. If this neuron fires and it's inhibitory, it makes this neuron less likely to fire. There's this constant push and pull between excitation and inhibition in the brain. There are connections between the brain. So which parts of the brain are physically connected to which other parts of the brain. So just like the Facebook example, where as a data scientist, you are trying to figure out, based on text and graphs and demographic information, what's the probability of a person clicking on an ad? We are taking data, huge amounts of data, doing text mining to figure out which parts of the brain are statistically related to which different phrases or ideas like memory and language. And we can map words to brain space by doing that. We can also take the physical connections, which parts of the brain are connected to which other ones, which is a graph, like a social network. We can also take which cells exist, what kinds of cells are in any given part of the brain. That's the demographic information, right? We can take all of these disparate data sets, and now we can bring them together in ways that people haven't been doing before, and we can sweep through huge amounts of data to try and generate new hypotheses, just like I showed you with the migraines and the striatum. But now we can do it using genes, cell types, connections, ideas, words, tasks, cognitive functions to brain, and map all of these things together and begin to try and find, are there certain genes that are statistically over or under expressed in the parts of the brain that are related to memory that we might have missed? Are there certain cell types related to language in the language parts of the brain that we've missed, that we couldn't find? So it's taking the same tools, the exact same math and techniques and code that people are using in industry at places like Facebook to try and figure out what makes us click on ads, which sucks, and trying to figure out how to make an understanding model of human cognition on this side of things. So that is the intersection. It turns out there's a lot of technical details under the hood, but that is the intersection in my lab between the data science and the neuroscience side of things. All right, everyone, thank you very much. Take care. Thank you, thank you.
Hello， 大家好，我是嘉贤布布。Disclaimer 放在前面，本视频不针对任何人种以及国籍，仅仅是对一种社会现象的阐述以及背后原因的探讨。在我高一的时候，我经常整夜的失眠，大概每周能睡20个小时就算是好的了。因为褪黑素不管用，而且没有车，所以去医院的话会很贵。再加上我是个愚蠢的高一学生等种种原因，我去了学校的心理咨询室。心理咨询室的老师给了我3条建议：做瑜伽、听音乐，别想那些有的没的。这完全没有用的3条建议，我却认认真真的奉行了1周。因为完全没用，所以我又去找咨询室的老师，然后告诉他这完全没用。咨询室的老师眉头一皱 ，Oh dear, I hope it does not affect your grades。然后他告诉我，如果情况持续恶化的话，我一定要告诉他。我忍着翻白眼的冲动走出了咨询室，迎面撞到和我关系很好的一个学姐。她看到我从心理咨询室出来之后，着急忙慌地跑了过来，问我发生了什么。我向她说明了情况之后，学姐告诉我，以后见到咨询室的老师的话，一定要告诉他我什么事儿都没有，因为这个名为心理咨询室的地方，它就是一个退学陷阱。我的学姐为我讲述了另外一个学姐的故事，那个学姐和我一样，因为长期失眠，所以选择去心理咨询室。结果呢，因为她的可能是成绩比较一般，所以被学校给劝退了。听到这里，我非常的恐惧，因为这样一来，我会不会被退学就要看我的成绩了。然后学姐安慰我说，只要我表现得非常的阳光、积极向上的话，应该就是没有问题的。 所以在高一的时候，我去报了表演课。后来呢，我在学校里遇到了几次这个咨询室的老师，我拿出了我几个月的表演功底，总而言之是蒙混过关了。再加上我成绩并不是那么看不过去，所以说我总算是没有被退学。到了高2的时候，我有一个同学，他因为被其他同学欺负之后，被心理咨询师的老师精准抓住，然后劝退了。是的，被劝退的不是施暴者，而是受害者。这下我彻底相信学姐说的话了。从那以后，我每天都离那个心理咨询师远远的。如果一个学生有心理疾病的话，他可能会自杀，然后成绩也可能会一落千丈。为了保证学校的名誉，心理咨询师做的是精准的找到学生中有这些心理疾病的，然后将其退学。他并不能帮助任何的学生，因为他的本质就不是为学生而服务的，他服务的是学校的名誉。